Welcome, ladies and gentlemen, to Integrated Math 2. In today's episode, we will be discussing Chapter 10.2.2, which is Angles and Arcs of Circles. With a lot of exposition in this first problem here, I would encourage you to pause and go ahead and read up a little bit about Eratosthenes and how his remarkable discovery, pre-existing all of our technology, allowed him to, in the 3rd century, essentially calculate the circumference of the Earth using a couple of sticks and shadows. It's a pretty interesting story. If you don't have time for it, there's actually a few YouTube videos that are only about 2 or 3 minutes long about how he was able to do that. But basically, this problem that we're dealing with in 10-61 lays out how he was able to do it, and those problems that you see summarized in some of those other videos about him. And actually, this problem kind of brings back some memories because it takes me back to my credentialing exam. This was a history of math free response question in one of the problems, so I thought it was pretty interesting that it would show up in a regular textbook. But basically, the story goes that Eratosthenes wanted to calculate the circumference of the Earth by using the distance between two cities, Alexandria and Syene. He was able to use a couple of proportions, use some geometry and some what was not called integrated 2 at the time, but integrated 2 math to roughly estimate to a pretty good level of accuracy the circumference of the entire Earth. So after reading all of this, exposition up top here, they talk about in part A, they say the precise data used by Eratosthenes was lost long ago. However, if he used a meter stick, because they weren't measuring things in meters at the time, but if he used a meter stick for his experiment today, then the stick's shadow in Alexandria would have been 127 millimeters long. And it says, determine the angle that the sun's rays make with the meter stick. And remember that a meter stick is 1,000 millimeters long. So what I'm going to do is I'm going to go ahead and paste this image down here. So this is part A. What they are basically asking us to do in part A is to use this small square right here and determine the angle theta right here. So I'll go and just expand him out again. And notice how he does make a convenient shape that is a right triangle. And so from here, they're telling us that the meter stick is 1,000 millimeters long. The meter stick is this diagonal facing upward side here. So I'm going to put the 1,000 right here. We know that the stick's shadow in Alexandria would have been 127 millimeters long. And I believe with this angle in mind, we could probably come up with a relationship that would link the two together. I know that tangent of that theta would be equal to 127 over 1,000, which would be opposite over adjacent. So if I wanted to get the theta alone, I would tan inverse both sides, and I get theta equaling, let's see, the tangent inverse, tan inverse of 127 over 1,000. So I am typing this into the calculator, and I had to kind of switch modes there. It was in a different calculation. And that is going to equal 7.2378 degrees. So that would be the measure of this angle right here, which is also the measure of, I'll switch colors, that way you guys can actually see it. That is also the measure of this angle right here. Cool, so we've already done part A. We're looking good so far. Now it says in part B, it says, assuming that the sun's rays are essentially parallel, determine the central angle of the circle if the circle passes through Alexandria and Syene. And how did you calculate your answer? So from here, I'm going to go ahead and you see these dotted lines right here, which are a lesser magnified version of these dotted lines. I will go ahead and carry on those dotted lines, and what they want you to see is they want you to see a relationship between this angle theta, which is essentially this angle right here, and this angle here. Now notice how they told you that those angles are that those lines are parallel. The fact they're parallel brings back an old friend, which we haven't talked about in a long time. This angle is an alternate interior angle. We haven't talked about that guy in a long, long time. Which means if the lines are parallel, then the angles are going to be congruent, which means the interior angle, the central angle of this circle, the central angle, will also be 7.2378 degrees. Very cool. So how does this help us? Well, it says since the distance along the Earth's surface from Alexandria to Syene is 500 miles, this is the same as the length of the arc between Alexandria and Syene. So what they're telling us is that this value here that I'm highlighting in purple is going to be 500. And it says, use this information to approximate the circumference of the Earth. So how does this help? Well, what I'm going to do is I'm going to set up a proportion. And the proportion is going to be a fraction equaling another fraction. So what I'm going to do is I'm going to say, all right, well, I know my central angle is 7.2378 degrees. So I can say 7.2378. And that's going to be a fraction of the total angles that form a circle, which is going to be 360. Well, I know that this 7.2378 degrees is correspondent to the 500 miles that is a fraction of the total Earth's circumference, which is exactly what they're asking us to find. So how much is the Earth's circumference? I have no idea. I'll go ahead and call him x. And what I'm going to do is I'm going to use these proportions. Remember, this is the proportion of the angles of the Earth versus the circumference of the Earth. So I'll go and cross multiply. I get 7.2378 times x equals whatever 500 times 360 is. That's going to be 180,000. And I'll go and divide by 7.2378 on either side. 7.2378. So the circumference of the Earth should be approximately 7.2378. Syntax error. I put two dots. Boom. 24869.435 miles. So not bad, considering he had no technology on him to calculate the circumference of the Earth. It's actually pretty close, because the actual circumference of the Earth in miles is actual circumference 24,901. And yes, I had to kind of pause to Google that one just to make sure that it was all good. Yeah, so we're looking pretty good here. And this 24,901 is found by satellite technology, which didn't exist back in the 3rd century BC. So definitely not bad using math to be able to get that close. So now we're going to go to part D for a second here, and we will go from there. Give me a second. It says to use your result from part C to approximate the radius of Earth. So circumference, right, is equal to 2 pi r. And so we know that r approximated, and I'm not going to use the actual circumference because this is our approximation right here. So I'm going to do 24869.435 is equal to 2 pi r. So I just have to take this number and divide it by 2 pi. So divide by 2 pi. And I'm going to get the radius of Earth is approximately equal to 3958.093 miles. So not bad, not bad. I like how we can use some pretty basic technology to find out the circumference of Earth and the radius of Earth. So, okay, this lesson actually is going somewhere. We're going to be talking about central angles and inscribed angles of circles. I will be back with the next problem. Give me a second, please. Okay, so in 10-62, they talk a lot about central angles. And so they tell us that to determine the circumference of the Earth, Eratosthenes used an angle that had its vertex in the center of the circle. Like the angles and polygons that you studied in Chapter 8, this angle is called a central angle. So in Part A, it says, an arc is a connected part of a circle. Every central angle has a corresponding arc. For example, in circle T at the right, this guy, angle STU, so this angle here, which is the 40-degree angle in the center, STU, is the central angle that corresponds to arc SU. That's what this little arc-looking thing means. It means arc SU. It says, since the measure of the central angle helps us to know that it is part of the whole 360 degrees of the circle, the arc can also be measured in degrees. So this part here is super important. They're telling us the measure of an arc is defined to be equal to the measure of its corresponding angle. Okay, so that is the meaning of this diagram right here when they talk about a 40-degree angle and a 40-degree arc. Now, keep in mind, that's the measure of that arc. It's not the arc length. They clarify that better in part B, but arc measure does not mean arc length, and you're going to make that mistake. You're going to get those confused on a quiz. Do not get them confused. Arc measure is the degrees that the arc contains, or the degrees that the arc takes. Arc length is going to be literally the distance between the 2 points on the arc, and they talk about that in part B. So it says, examine the circle above. What is the measure of SU, written as the measure of arc SU? Well, the measure of arc SU is going to be 40 degrees. I think they told us that. The measure of arc SU is going to be 40 degrees. Now, they say, what is the measure of arc SZU? The measure of arc SZU? Well, notice how the Z is in between. What are they trying to tell me? Well, they're trying to tell me that I got to go the other way because I actually have to hit that Z point right there. And so they want the larger arc measure. Again, they don't want the arc length. I'm not doing the theta over 360 times 2 pi r. I'm not doing arc length. I'm doing arc measure. So what I want is I want the measure in degrees of how much arc does that take. Well, if the measure of arc SU is 40, that means that there's 320 degrees left over for SZU to take. And how did I get that? Well, that's going to be 360 minus the 40 that was already being taken by arc SU. It says in part B, when Eratosthenes measured the distance from Syene to Alexandria, he measured the length of an arc. This distance is called an arc length. So here we are. We're back to arc length again. It says measured in units of length like centimeters or feet. One way to measure an arc length is to wrap a string around a circle and straighten it up to measure its length. However, if the figure is not drawn to scale, you must calculate the arc length using other information. We already have a formula for this. And so they want us to calculate the measure of arc SU if the radius is 12 inches. So we know this. This should be 40 degrees occupied of the 360 degrees total times 2 pi r would give us the arc length. So from here, let's go ahead and simplify this. That's going to be 1/9 times 24 pi. These guys both divide into 3, so I'm going to get 8 pi over 3. In this case, they're not telling me... Oh, inches. Here we go. Inches. Now again, what they're trying to get at is that the arc measure is measured in degrees, but the arc length, right? This is the arc length. Well, that's still going to be measured in feet or miles or inches or millimeters or whatnot. This is measured in degrees. Okay, that'll wrap up that problem. I'll come back with inscribed angle next. I'll be right back. In 10-63, they talk about the diagram BDC. They're telling you about the inscribed angle, which is the angle whose vertex lies on the circle. And it says it corresponds to the central angle BAC because they both intercept the same arc. So again, notice how angle D and angle A, they both intercept that BC, that arc BC. So that's why angle D is considered an inscribed angle. Angle A is considered a central angle. Right? It says, investigate the measure of inscribed angles using the question below. It says, in the circle at the right, angles F, G, and H are all examples of inscribed angles. Notice that all three angles intercept the same arc, JK. Let's see if that's true. Angle F, right, definitely intercepts that JK. Angle G, in a bit of a different way, it still intercepts that JK. And angle H still, again, intercepts that JK. Well, what are you supposed to notice? Well, at this point, you're kind of supposed to get into your groups and use tracing paper. But what you are supposed to get out of that is that when you trace each angle and measure its angle, what you'll find is that all three angles will be congruent. And you're supposed to do that using tracing paper, but I'll go ahead and give that to you. All three angles are congruent. So with all of them being congruent, as long as they, and they're in, notice how they're in different locations, but as long as they intercept the same arc, they will be congruent. So now let's find out how the inscribed angle and central angle are related. And again, you're supposed to use tracing paper again for this one, as it says in the instructions here. It says compare a central angle with its corresponding inscribed angle. What's the relationship that you notice? what you're supposed to notice, and again, I'm just gonna have to give this to you because I can't really use tracing paper on this program, is that the inscribed angle is 1/2 the measure of the central angle. So you're supposed to get that out of it. So for example, if the measure of angle Z was to equal 80 degrees, that means then that the measure of angle X would be equal to 40 degrees. If the measure of angle Z was to equal 120 degrees, then the measure of angle X would be equal to 60 degrees. So the inscribed angle will always be 1/2 the measure of its corresponding central angle, which is actually the same as its corresponding arc, right? So if I said to you that the measure of arc WY was equal to 100 degrees, well, that's exactly like saying the measure of angle Z would be equal to 100 degrees, because we talked about it a few seconds ago, right? How the measure of the central angle and the measure of the corresponding arc were the same. So if I was to say, okay, based off of that, what is the measure of angle X? You could then determine that the measure of angle X would be 50 degrees as well. Okay, let's go and do an example of this, and then we'll be good. Okay, now that we've got this, these two ideas under our belt, let's go and do some examples of inscribed and central angles. I'll go and make some space right there. So it says, examine the diagrams below. What are the measures of the indicated arcs or angles? If a point is labeled C, assume it is the center of the circle. So in part A, we have this arc being 118 degrees, which means this X is its corresponding inscribed angle. So what I have to do is take X to be 118 degrees, and I got to divide that by 2. So 118 divided by 2 is going to be 59. 59 degrees. In B, they're making me move backwards now. Now they're giving me the inscribed angle. Now I have to go back and find the arc. Well, remember, the arc, so if the inscribed angle is half the measure of the arc, that means that the measure of the arc would be double the value of the inscribed angle. So X would be 41 times 2, which would be 82 degrees. Again, we're finding arc measure, right? We're not finding arc length. We're finding arc measure. So part C gets a little more complicated. We got to solve for X, Y, and Z. Well, the first thing I'm going to do is I'm going to find out the measure of this angle right here. And the way I'm going to do that is I'm going to use my good old triangle angle sum theorem. And so I'm going to find out that that's 180 minus 90 minus 78. So that makes this small red angle here 12 degrees. Hopefully you can see that. Well, this 12 degrees is the inscribed angle for letter Z. So Z has to equal 24. Y is the corresponding arc to this inscribed angle right here, which is 78 degrees. So 78 times 2 is going to be 156. And X is the corresponding arc to this inscribed angle, which is 90. So it's got to be 180. And if you added those up, they do in fact equal 360. Awesome. Let's keep on moving. All right, 56. Well, I know that X is the correspondent arc, so I know that X is 56. Y is going to be half of that at 28. Right, so again, 56 divided by 2. This one's a little bit tricky. It's visually off-putting. X is going to be 114 because of the correspondent central angle to arc length. But notice how Y is the inscribed angle to that 114, which makes Y 57, which is 114 divided by 2. And now from here, if you look at 28 and Y and X, X would be 56. Hopefully we're getting faster at this because X would be double the inscribed angle. Y would be 28 because these both inscribed angles correspond with the same arc. And that will wrap it up for this lesson. Hopefully you got a lot out of that. Just always remember the arc measure and arc length are different things. and that the central angle's measure will always be the same as the arc measure, and that the inscribed angle will be half the central angle and or half the corresponding arc measure. So that'll wrap it up for this video. As always, please leave questions or comments in the comments area, and I will see you all in the next episode.